Why does everything around us generate sound? And also there are a whole variety of sounds like cell phone, running faucet, water, and music instruments, someone's voice. The list of sounds you hear throughout a given day is endless. But when given to describe what sounds looks like, it always ends up like this, which sounds like this. And to me, that doesn't make much sense because you never hear the sounds in real life. In this discussion, let's try to better understand what is sound. Let's start with a simple sound. That was a popping and inflated balloon. This balloon is filled with high pressure air particles. When popped, all these particles rushed out and hit adjacent air particles. Those particles hit the next set of adjacent particles and so on, thereby creating an expanding shell of air particles just bouncing into one another. This is called an air pressure wave or sound wave. This wave travels, which causes parts of your internal ear to move. Then your brain processes this motion in your internal ear and tells your cognition that, oh, this motion in my ear sounds like a popping balloon. Let's review back and how does the sound motion really works in more elaborate terms. Even through popping, the balloon makes a relatively simple sound. When we take cross-section and zoom in on a molecular level, we can see the complex pattern depicting how the air particles are bouncing to one another. We know that vibration is nothing but a to and fro and back and forth vibration that produces sound. So if we set any body into vibration, it will give us some sound vibrations. And membranes of the dialect which produces sound in the music instrument, like the sitar and the guitar. It is the vibrations of strings when left that reduces the sound. These vibrations are then transferred to the soundboard, which adjusts the loudness of the sound. This pattern is produced within the tenths of a second after the balloon is popped. You may ask, where does this pattern come from? Well, the high pressure air particles rushed out and generate a high pressure wave. When they do, they create a low pressure void in the balloon center. Imagine changing the speed of the wave. The speed of the wave changes as it enters different medium and the frequency remains the same. But the wavelength changes, the frequency cannot change as it is set by the high pressure of the balloon. So as speed increases, wavelength increases. As speed decreases, wavelength also decreases. This is a slinky toy. It may demonstrate on how sound wave works through compression and rarefaction. The fundamental concept of sound wave, the air particles rush back into to fill this void and therefore generating a low pressure wave. When the particles rush back into fill the void, they rush in too much, thereby creating a second high pressure zone. This cycle repeats itself, and each time it does generates a high pressure and low pressure wave which can be graphed. This graph shows the pressure waves of waveforms produced by a popping balloon. The vertical axis pressure, or the amount of force the particles bound into one another. The horizontal axis is time. These high points in the waveforms are called compressions, and they are where the particles are compressed and bounce a lot, thus having a higher pressure. The low points in the waveforms are called rarefactions, and they are where the air particles are more spread out and not bouncing around as much, and thus have a lower pressure. To help you visualize how sound waves of a compression state and rarefaction state, a shockwave of an explosion does these characteristics. Prior to an explosion, the shockwave pressure has a devastating effect on the surrounding environment. In this case, the pressure was measured by a microphone in order for a speaker to duplicate the sound. The diaphragm in the speaker just have to move in a similar fashion. The entire sound takes of 1/10 of a second for a speaker to duplicate. This visualization is just the first section of the overall pattern popping balloon of cycling compression and rarefaction produced by popping balloon. In just this quick sound, there were about 50 of these cycles. If we slow down this sound to 4 seconds, you can hear a rumble sounds of the cycles between compression and rarefaction. Most sounds last much longer than this quick duration. In visualization of sounds, we usually see the squished version of this graph which looks like this. Let's consider another sound, which is a running faucet. The moving water molecules apply a force to the nearby particles, thereby causing the air particles to bounce into one another, thus creating another sound. The air particles are moved, which can be seen in the shape of a waveform. Another difference is that the sound of the running water is continuous, whereas the popping balloon only lasted a span of a second. Beethoven 9 Symphony. Let's consider another more complex sound for an example of learning of sounds. This is the sound of a Beethoven's 9. It's constructed from dozens of instruments. Each instrument, when played, applies a force to the air particles and around it, thus causing the air particles to bounce into one another, thereby generating a sound wave. So when these waveforms of different instruments meet in the air, they combine to make new unique waveform of sound. Wait, let's us just rewind and clarify three important things. First, this animation properly shows how a sound wave is a sequence of alternating compression and reflections. However, it does not show how sound propagation in all directions. The sound propagates kind of like this, as an expanding sphere. So just keep in that mind. Also, second, with this animation, it looks like the particles are traveling. However, in reality, it is the force of air particles that is traveling, and this propagation of force along with the alternating compressions and rarefactions is what constitutes a sound wave. Take a look at the video of how sound travels to better conceptualize this bouncing-like movement of air particles. And finally, third, this sound wave is just a quick snapshot of what the entire sound wave looks like. It's about 4 thousandths of a second in the duration. To say differently, there will be 440 of this waveform hitting your ear in 1 second. Or to say technically, the frequency of this violins is 440 Hz. Or musically, it is the musical note A. Okay, now we have those details clarified, let's jump back to where we were. So when the waveforms of different instruments meet in the air, they combine to make a simple combination of instruments. Our brain is able to analyze this combined waveform and pick out individual instruments. However, when many instruments are combined, only a trained ear would be able to determine all the instruments used to create the music, because the combined new waveform is so dissimilar to the individual instruments. Furthermore, for us to record and play back the sound of Beethoven's 9, we would just need to convert the pressure waveform in the concert hall into something like a string. This is the core concept of a styrofoam cup. A device measures the force or pressure levels from the air particles in the holding cup or tin cans and transmit them into the string connecting the holding cup membrane. You can see how the shape string closely of the graph waveforms we have been talking about. To play this game, two cups just need to follow with an attached string and convert this motion into the motion of a waveform, which applies a force to the air particles, thereby reproducing the original sound. Thanks for joining us to learn more about sounds. If you have any further questions, please post them after this video. And do share what you have learned about sounds to your families and our friends. Thank you.